Which hash function am I using? How can you tell if the software library you are using implements FIPS 202 SHA-3 or CATCHEK 256, if both might be called SHA-3? An easy way to tell is to use a test vector, an expected output for a given input. The test most commonly used for a hash function is the empty input. If you run the hash function with an empty string as input, you should see the following results. CATCHEK 256 of empty string equals C5D24 470. SHA-3 of empty string equals A7FFC 34A. Regardless of what the function is called, you can test it to see whether it is the original CATCHEK 256 or the final NIST standard FIPS 202 SHA-3 by running this simple test. Remember, Ethereum uses CATCHEK 256, even though it is often called SHA-3 in the code. Note: due to the confusion created by the difference between the hash function used in Ethereum and the finalized standard, there is an effort underway to rename all instances of SHA-3 in all code, opcodes, and libraries to CATCHEK 256. See ERC59 for details. Next, let's examine the first application of CATCHEK 256 in Ethereum, which is to produce Ethereum addresses from public keys. Ethereum addresses. Ethereum addresses are unique identifiers that are derived from public keys or contracts using the CATCHEK 256 one-way hash function. In our previous examples, we started with a private key and used elliptic curve multiplication to derive a public key. Private key small k equals F8F8 . Public key big K, x and y coordinates concatenated and shown as hex. Big K equals 6E145 E5E . Note: it is worth noting that the public key is not formatted with the prefix 04 when the address is calculated. We use CATCHEK 256 to calculate the hash of this public key. CATCHEK 256 of big K equals 2A5BC ... 0F9. Then we keep only the last 20 bytes, least significant bytes, which is our Ethereum address, 001 ... 0F9. Most often you will see Ethereum addresses with the prefix 0x that indicates that they are hexadecimal encoded, like this, 0x001 ... 0F9. Ethereum address formats. Ethereum addresses are hexadecimal numbers, identifiers derived from the last 20 bytes of the CATCHEK 256 hash of a public key. Unlike Bitcoin addresses, which are encoded in the user interface of all clients to include a built-in checksum to protect against mistyped addresses, Ethereum addresses are presented as raw hexadecimal without any checksum. The rationale behind that decision was that Ethereum address would eventually be hidden behind abstractions, such as name services, at higher layer of the system, and that checksum should be added at higher layers if necessary. In reality, these higher layers were developed too slowly, and this design choice led to a number of problems in the early days of the ecosystem, including the loss of funds due to mistyped addresses and input validation errors. Furthermore, because Ethereum name services were developed slower than initially expected, alternative encodings were adopted very slowly by wallet developers. We will look at a few of the encoding options next. Inter-Exchange Client Address Protocol. The Inter-Exchange Client Address Protocol, ICAP, is an Ethereum address encoding that is partly compatible with the International Bank Account Number (IBAN) encoding, offering a versatile, checksum, and interoperable encoding for Ethereum addresses. ICAP addresses can encode Ethereum addresses or common names registered with an Ethereum name registry. You can read more about ICAP on the Ethereum wiki. IBAN is an international standard for identifying bank account numbers, mostly used for wire transfers. It is broadly adopted in the European Single Euro Payments Area (SEPA) and beyond. IBAN is a centralized and heavily regulated service. ICAP is a decentralized but compatible implementation for Ethereum addresses. An IBAN consists of a string of up to 34 alphanumeric characters, comprising a country code, checksum, and bank account identifier, which is country-specific. ICAP uses the same structure by introducing a non-standard country code, XE, that stands for Ethereum, followed by a 2-character checksum, and 3 possible variations of an account identifier as described below. 1. Direct. A big endian base 36 integer comprised of up to 30 alphanumeric characters, representing the 155 least significant bits of an Ethereum address. Because this encoding fits less than the full 160 bits of a general Ethereum address, it only works for Ethereum addresses that start with 1 or more 0 bytes. The advantage is that it is compatible with IBAN in terms of the field length and checksum. Example: XE60 ... KJD, 33 characters long. 2. Basic. Same as the direct encoding, except that it is 31 characters long. This allows it to encode any Ethereum address, but make it incompatible with IBAN field validation. Example: XE18 ... U2P, 35 characters long. 3. Indirect. Encodes an identifier that resolves to an Ethereum address through a name registry provider. It uses 16 alphanumeric characters, comprising an asset identifier, for example ETH, a name service, for example XREG, and a 9-character human-readable name, for example kitty cats. Example: XE #, ETH, XREG, kitty cats, 20 characters long, where the #, should be replaced by the 2 computed checksum characters. We can use the help ETH command line tool to create ICAP addresses. You can get help ETH by installing it with npm install-g help ETH. If you don't have npm, you may have to install Node.js first, which you can do by following the instruction at nodejs.org. Now that you have help ETH, let's try creating an ICAP address with our example private key, prefixed with 0x and passed as a parameter to help ETH. Help ETH key details -p 0xF8F8 ... 315. The output is the following: 1. Address 0x001 ... 0F9. 2. ICAP XE60 HAMI ... HWKJD. 3. Public key 0x6E145 ... 07B ... The help ETH command constructs a hexadecimal Ethereum address as well as an ICAP address for us. The ICAP address for our example key is XE60 ... HWKJD. Because our example Ethereum address happens to start with a 0 byte, it can be encoded using the direct ICAP encoding method that is valid in IBAN format. You can tell because it is 33 characters long. If our address did not start with a 0, it would be encoded with the basic encoding, which would be 35 characters long and invalid as an IBAN. Tip: the chances of any Ethereum address starting with a 0 byte are 1 in 256. To generate one like that, it would take on average 256 attempts with 256 different random private keys before we find one that works as an IBAN compatible direct encoded ICAP address. At this time, ICAP is unfortunately only supported by a few wallets. Hex encoding with checksum in capitalization, EIP55. Due to the slow deployment of ICAP and name services, a standard was proposed by Ethereum Improvement Proposal 55, EIP55. EIP55 offers a backward-compatible checksum for Ethereum addresses by modifying the capitalization of the hexadecimal address. The idea is that Ethereum addresses are case insensitive, and all wallets are supposed to accept Ethereum addresses expressed in capital or lowercase characters without any difference in interpretation. By modifying the capitalization of the alphabetic characters in the address, we can convey a checksum that can be used to protect the integrity of the address against typing or reading mistakes. Wallets that do not support EIP55 checksums simply ignore the fact that the address contains mixed capitalization, but those that do support it can validate it and detect errors with a 99.986% accuracy. The mixed capitals encoding is subtle and you may not notice it at first. Our example address is 0x001.0f9. With an EIP55 mixed capitalization checksum, it becomes 0x001.0F9. Can you tell the difference? Some of the alphabetic A to F characters from the hexadecimal encoding alphabet are now capital, while others are lowercase. EIP55 is quite simple to implement. We take the catcheck 256 hash of the lowercase hexadecimal address. This hash acts as a digital fingerprint of the address, giving us a convenient checksum. Any small change in the inputs, the address, should cause a big change in the resulting hash, the checksum, allowing us to detect errors effectively. The hash of our address is then encoded in the capitalization of the address itself. Let's break it down step by step. 1. Hash the lowercase address without the 0x prefix. Catcheck 256 of 001.0F9 equals 23A.AE1. 2. Capitalize each alphabetic address character if the corresponding hex digit of the hash is greater than or equal to 0x8. This is easier to show if we line up the address and the hash. Address 001D3F ... hash 23A69C ... Our address contains an alphabetic character D in the fourth position. The fourth character of the hash is 6, which is less than 8, so we leave the D lowercase. The next alphabetic character in our address is F in the sixth position. The sixth position of the hexadecimal hash is C, which is greater than 8. Therefore, we capitalize the F in the address, and so on. As you can see, we only use the first 20 bytes of the hash as a checksum, since we only have 20 bytes in the address to capitalize appropriately. Check the resulting mixed capitals address yourself, and see if you can tell which characters were capitalized and which characters they correspond to in the address hash. Address 001D3 big F ... hash 23A69C ... Detecting an error in an EIP55 encoded address. Now, let's look at how EIP55 addresses will help us find an error. Let's assume we have printed out an Ethereum address which is EIP55 encoded. 0x001D3 big F1E ... Now let's make a basic mistake in reading that address. The character before the last one is a capital big F. For this example, let's assume we misread that as a capital big E, and we type the following incorrect address in our wallet. 0x001D3 big F ... 0 big E9. Fortunately, our wallet is EIP55 compliant. It notices the mixed capitalization and attempts to validate the address. It converts it to lowercase and calculates the checksum hash. Catcheck 256 of 001.0E9 equals 5429.927. As you can see, even though the address has only changed by one character, the hash of the address has changed radically. That's the property of hash functions that makes them so useful for checksums. Now, let's line up the two and check the capitalization. Address 001 small d ... hash 5429 small b. It's all wrong. Several of the alphabetic characters are incorrectly capitalized. Remember that the capitalization is the encoding of the correct checksum. The capitalization of the address we input doesn't match the checksum just calculated, meaning something has changed in the address, and an error has been introduced. Conclusions. In this chapter, we provided a brief survey of public key cryptography and focused on the use of public and private keys in Ethereum and the use of cryptographic tools such as hash functions in the creation and verification of Ethereum addresses. We also looked at digital signatures and how they can demonstrate ownership of a private key without revealing the private key. In the wallets chapter, we will put these ideas together and look at how wallets can be used to manage collections of keys.